Welcome to the fourth edition of this series of videos. I'm sort of redoing Professor Lewin's 802 physics videos. Not redoing them, but just adding a context of maybe it happens for some other reason. Just offering alternative explanation. Definitely pointed to what I think is the correct answer, and essentially answering questions that they don't answer in these lectures and such. So we'll play a little bit of this is the experiment we concluded with in the last video, and I'll just explain what I think is really happening here.
That is not so important. What is in a name after all? But it happens to be negative. Okay, so now we go here. I bring it here. I hope that no sparks will fly over because that ruins the demonstration. And now, notice what I do. While the rod is here, I separate them.
Okay, so it's two metal balls, probably aluminum, paramagnetic rather than ferromagnetic for good reasons. But anyway, separated. Oh, I have to put the drawing on. There's a lot to. You really have to keep your wits about you. Can't get the least bit lazy here. No, that looks okay. All right, hopefully we're working. I hate doing these over, as happened. Let's see. Starting over anyway. Okay, so you have two metal balls, and what you do is you connect them. So we'll just use, he has them touching, but it doesn't matter. You connect them, and then you disconnect them. And the idea is you bring something charged. All right, so he said it was negatively charged, so we'll go with what he said. So this is negative, 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 negative. And the idea is what's going to happen is obviously this is going to tend to go positive. That is, the electrons are going to start running away. So these are all little positives here, and then this will be all negatives down here. And that's really not exactly the best way to describe what's happening, because it's really the pressure argument. And so to illustrate it, and what you really want to do is just follow the electrons. The protons are sort of irrelevant because they're just not, they're not terribly relevant to understanding the electrical component of magnetism. Let's just put it that way. So you can sort of understand, let's say I just make a triangle and I say this is the area that electrons are in the normal atoms. And what's really happening is there's a certain amount of space that now will be occupied. All of those electrons will now be occupying that smaller space because they're all, in this case, they're running away. So it would have been better if it was a positive stick than But anyway. So the ones at this end are running away, and so they're compressing because they're in a smaller space. Get it? So that's higher pressure. Now the atoms that those electrons are part of have more pressure in them because they're pushed into a smaller space, which has increased their pressure. So in a sense, what is taking place here is that this is becoming high pressure, electron pressure, and this is low electron pressure at this end. And because he didn't touch it, and that's important. If he would have touched it, then the whole thing would have become negatively charged. Everything just would have gone negative right away. And when you separate them, you just get a negative ball and a negative ball. But the fact that he didn't touch, but he's inducing, means that the thing's moving and it starts off as a dipole. It wants to be one, in a sense. So anyway, but it's just a pressure gradient in a sense. So I would illustrate it. I should see if this is showing, so I have to look at the other thing. Yes, so we're close enough to being visible. So what it really is a linear thing. So we go from low pressure to high pressure. And as I was pointing out before about this, when does two things become the same size? Right, so at a certain distance. Oh, that camera's on. Okay, say why. So these are really different. Okay, but I can make them look the same size. When they're the same size, that's like ground. That's the neutral. If I move this one a little forward, I move this one a little backward, then I break that. So become plus and minus. This finger gets big again, or it gets smaller. So it's linear from low pressure to high pressure, and technically there's a ground on that linear line, in the middle. So if you thought of this as being a 10 as a total, you could say that now once he breaks it, okay, he separates the linear line, then what you have really is one ball is going to be the average of this, which is like say an 8, which to ground, which is going to be a 5, that would be a +2, and this is going to be the other ball, and it's going to be averaging out from its low pressure, and could end up something like a -2 from ground. And so you've created two opposite charged objects. You've separated the dipole that you were inducing. And you can only induce it. You can't, if you attempt to directly create it, you won't. So like I said, if you touched it, you would have ruined it. If one of the balls was twice as big as the other one, then you would have a disproportion in that charge. Then this, the big one would occupy more of this average, and so the diluted total would be some much lesser differential from ground. I think that's all I need to add to that. Yeah, so there were two things at least that he could have demonstrated or explained. The fact that why he doesn't touch it, because that would make it a monopole, and that if you change the size of these things, you will change the average number, and so they will average to a different charge. Yeah. Okay, so enough drawing, and back to the videotape.
So as I was holding it there, things were going on in there that you and I couldn't see, but the electrons, the rubber rod is negative, electrons were shifting in this direction, and this is now positive and that is now negative. If I take this one...
So he said shifted, so that's good. That sort of just implies they're not doing a lot of moving. But later he's going to probably say the magic word, moving.
And I touch it with the electroscope. You clearly see that there is charge on this. How can I show you now that there is charge of different polarity on the other one? Well, the way I will do that is I will approach this electroscope by bringing this sphere very close to it. And if this charge is different than the charge that is on it, the electroscope will, the reading will become smaller. And why is that? Why will the reading become smaller? Well, here is the situation of the electroscope now. And here is that ball that you see on top. This is upside down there. If this is all negative,
yeah.
That's why it is apart. If now I approach this here with an object which is positively charged, and I claim that this one now is positively charged because this one was negatively charged, the electrons love the positive charge, so the electrons want to come to the positive charge, so these electrons drift down again. And so if they come down, fewer will be here, and so you will see this. If, however, I put here a negative rod...
So clearly it's the electrons that are the dominant players. The protons, in a sense, are moving indirectly because of the electrons. So, I mean, the electrons are moving. I mean, the protons are also moving. But again, they're not part of electricity. So, they don't have as much relevance. Their function is only in magnetism. They don't really do anything with electricity or, say, photons and all of that stuff. Photons interact with the electrons. The protons are kind of irrelevant.
Then the electrons which are here want to go further away, they will stream up, and therefore...
So they really don't stream up. They just, again, they pressurize. More of them do move into a smaller amount of space. They compress, and that creates pressure, and it's the same kind of pressure that is electricity.
The reading will become larger. So you can always, through induction, test what the polarity is of your charge. let's hope that this one is still holding its charge while I was talking. So I claim now that if this polarity is different, and if it's still there, when I approach the electroscope, come very close, that the reading should become a little smaller without even touching it. Let's see whether that works. You see, it goes down. You see, it goes down. It goes down.
Not very dramatic.
So through induction, I have demonstrated that this has indeed a different polarity from this one. If I approach it with this one, it would go further out, unless it already is at a maximum. Let's try that. You see, it goes further out. So not only have I demonstrated that I created a dipole, but you've also seen that by means of induction, that you can demonstrate that there's a difference in polarity between the two spheres. If I create a dipole, and I put that dipole in an electric field, the dipole will start to rotate. Let's first talk about it, why it rotates, and then I will try to demonstrate that by making a dipole. A big one, this big, right in front of you, almost as big as the one there. So let's have a...
So this making of a dipole by his definition, okay? I mean, he's using kind of a narrow definition of a dipole in the sense he's just basically saying I can call it a dipole if I put a positive charge here. If I take up two balloons and I charge one positive and one negative and put them on a stick, I made a dipole. Technically, that's not a dipole because it's not connected in a direct way. So it's sort of cheating the argument. I mean, a magnet is a dipole because you can't break it into anything other than dipole, dipole, dipole. No matter where I break it, it's a dipole again. So it's sort of cheating. Atoms are dipoles, but you can't really break them.
An electric field, like so. And I bring in this electric field a dipole, a biggie. Here, this is the one I'm going to use for this demonstration. Ping pong balls on either side, they are conducting, and they are connected with a rod which is not conducting.
So
here is this dipole.
Just two balloons on a stick.
So this rod is not conducting, and this is conducting, and this is a conductor. And let's suppose this is positive, and this is negative for now. And I'll show you how we get a charge on it. Well, the positive charge will experience a force in this direction, always in the direction of the electric field, and the negative charge will experience a force always upstream. And now there's a torque on this.
So, and I would argue that that's not what's really happening. It has nothing to do with any kind of streaming stuff. It has to do with the little bits and how many little bits are going to be hitting it of the color that they are. So there's going to be more positive bits, you could say, more red energy, and so the red thing's going to go with the flow, and there's going to be not much of the black stuff, so the black stuff's going to go the opposite way. It's a magnetic. It's going to move based on the orientation of the monopole. The monopole of negative is going to attract negative and repel positive. It's just, pretty simple.
And when there's a torque on this dipole, it will start to rotate clockwise. And of course, if it overshoots the field lines, when it is in this direction, the torque will reverse. It's very easy to see. And so what you will see, it's going to oscillate, and if there's enough damping, it will come to a halt more or less in the direction of the field lines. And this is something that I can demonstrate. First, I have to make a dipole of this kind. And the way I will do that is the following.
So there's lots of ways you could have done it. Like I say, you could just take the two balls. It's a little harder to put an insulator. Yeah, it's a little harder to hold them. But he could have put them on strings, charged them, and then just dangled them from a stick with the strings. But they're just the idea is that they're just really two monopoles on a stick. It's not really a dipole.
This is a metal bar. This is insulator. And here is there's these two ping pong balls. The one on this side has a yellow marker, the one on that side has an orange marker. And I'm going to attach them, holding them up against this metal bar. In other words, here is this dipole. It's not a dipole yet. Metal, and here is a metal bar. This is a conductor, which connects them.
So again, it's the same as the other experiment, except he didn't use a metal bar to connect the two spheres. He just touched the two spheres to each other. So in a sense, he could touch the two spheres to each other and do the same thing, but the catch would be that because they're such a small distance, you'd get a very weak dipole. So to get a stronger dipole, you have to separate them. The more you separate them, the better your dipole. The more distance from the positive end to the negative end when you create the dipole, the more extreme the difference between the two averages.
I'm going to turn on the Van de Graaff here. And the Van de Graaff creates an electric field. So we have the Van de Graaff here. Let's suppose that this Van de Graaff creates positive charge. Sometimes the Van de Graaff creates positive charge on the dome. Others can be designed to create negative charge on the dome. And remember, for now, I assume that's positive. What will happen now? Electrons want to go in this direction. So this becomes negative. Protons, positive charge stays behind. So that becomes, through induction, a dipole. Because I have them connected. I have them connected with this metal bar.
So, and importantly, he has them in a very high voltage. So by the R squared thing and everything else, it does create more of a differential in the voltage they're being exposed to. So the one closer to the Van de Graaff is being exposed to, say, 100,000 volts, and the one further away is down to already 25,000 volts. So it's a big differential in the voltage that they're going to be exposed to. That means the amount of monopole pressure. So the plus pressure is going to be thick where that first one is, and it's going to be thinner where the other one is. So one's going to get pressurized a lot, the other is going to get pressurized less. And again, he has the stick, so just understand that it's one thing, and it will be linearly affected. More at one end, lots of effect, less at the other end. I mean, more pressure at one end, less pressure at the other end, less electron pressure. So near zero at one end and the maximum at the other end. And then there'll be a neutral between those two, and the two balls will be averages from that neutral.
So these electrons can flow through this bar and end up here. Now?
So he says they flow through the bar. So right there I'd say I contend no, that never happens. The only thing that happens is the degree of pressure travels through the bar. So at one end of the bar it's more pressure, the other end there's less pressure, just like a wire in voltage. There's more pressure at one end of the battery and less pressure at the other end of the battery, and the wire has exactly that pressure differential built into it in a sense too. It will acquire that differential.
I remove the bar. And so when I remove the bar, I have created now a dipole. I have here an insulating thread, and I have a fishing rod, and at the end of my fishing rod, I have now a permanent dipole.
It's not a real dipole, again, just for clarity. It's a fake dipole, but yes, an imitation dipole.
With that permanent dipole, I'm now going to probe the electric field around this Van de Graaff. I could have chosen the same Van de Graaff, but there's a reason why I picked this one. And as I walk around this Van de Graaff, you will see that this fishing rod, at the end is this dipole, that the dipole always wants to go radially inwards or outwards, depending on how you look at it, of this field. So I can probe this field and make you see for the first time that there is indeed, somewhere here, a strong radial field going in or out of the Van de Graaff.
I don't know why he chose, other than the big one makes it more obvious. You know, the field is bigger.
And now comes something very interesting, which I found out this morning for the first time when I did this experiment. If the other Van de Graaff there is also positive when I run it, how do you think this dipole is going to align then if I walk into it? Will the negative ball be closer to the Van de Graaff, or will the positive one go closer to the Van de Graaff? So I give you 30 seconds to think about it. So I make the dipole as it is here. Let's assume this one is positive, this Van de Graaff. So this side becomes minus, I call that A, and this side becomes positive, that's B. I now walk with this dipole, I bring it in this field.
He's acting as if it's a trick question, so I guess, you know, the obvious answer is if this Van de Graaff is producing, as he's saying, negative, then the positive end is going to point towards the Van de Graaff. Trick question.
And let's assume that one is also positive. We don't know that yet. How,
Well, I thought you said it wasn't, but anyway, you already knew it was the opposite. Well, whatever.
how will the dipole align now? Will A go inwards or will A go outwards? Who thinks A goes inward? Very good. Who says A goes outward? Okay, A will go inward if the two Van de Graafs have the same polarity. So if that doesn't happen, that doesn't mean that physics doesn't work. It means the two Van de Graafs have different polarities. And we'll see what happens.
You really should know, because the Van de Graaff is just a machine, and it only creates an opposite polarity if you reverse or change what's rubbing against what.
So let me first then create a dipole. So here is the dipole. It's sorted out now. I turn on this Van de Graaff. So induction takes place. Remember that the yellow is pointing towards the Van de Graaff, and that the orange is away from the Van de Graaff.
So again, we have to try to figure this out. So the yellow is the one now that's getting negative because it's a positive Van de Graaff. Negative means less pressure there, more electron pressure at the other end. So, yeah. Okay.
Okay? So I induce a dipole. Oh, I really should redo that. I don't know what happens when it... I have to remove the field first. Okay. The yellow was inside, right? Was that the way it was? Okay. Yellow inside. There we go. So now it's creating a dipole through this metal bar. And I break contact.
All right, so he only used induction. He never touched it with anything. So again, it's a linear pressure that's now been put through both. One ball now is stuck with the low end pressure, and the other ball has the high end pressure, electron pressure. But the electrons haven't all moved to one end and all moved to the other end. It's just the atoms have all bent.
This should now be a dipole. Now I turn on the field of the... So if the polarity is the same, yellow will go in. I will try to swing it a little. Notice two things. It's going to line up beautifully radially.
Hasn't charging up very fast. Should let it charge up first before he walked in. But anyway, just my little critique.
But the yellow is not in. The yellow is out. So the two Van de Graafs have different polarities. But you will see they rotate nicely. And they end up beautifully radial. And when I go all the way around here...
Doesn't really work on fillium. I mean, you can't get the dimensionality to tell. So maybe you should use a flashlight or something.
Again, they may swing a little, they may oscillate a little, but through damping they will come to a halt. And look, the field is indeed beautifully radial, and the yellow is pointing outwards. The two Van de Graafs have different polarities. So you've seen how we can create a dipole, and you've also seen how we often can make statements about the specific polarity. I can probe an electric field using grass seeds in oil. Grass seeds are elongated, and when I put a grass seed in an electric field, it will become polarized. There's nothing you can do about it. Here's a grass seed, and the electric field is like so. And so the electrons want to go as far away in this direction as they can through induction, and so this side we may...
So I suppose he's saying that grass seeds are kind of ferromagnetic, like an iron filing, and so you can use them like an iron filing.
It's positive, and so what is this grass seed going to do? It's going to rotate. It's going to line up with the electric field.
And there's no electric field, there's just a magnetic field, a charge field.
And this is the way that I'm going to show you now field configurations in the vicinity of a dipole, and I will also show you then field configurations in the vicinity of two charges which have equal polarity. You may have seen this in high school with magnetic fields, with iron files. That's kid stuff. That's the easiest thing to do. This is the real thing. This is the electric field. I bet you've never seen...
Yes, there's no electric field. I'm sorry. It's just a magnetic field. It's just charge. Charge, charge, charge. It's electron pressure, proton pressure. There's no other kind of thing you can make. That's the only thing there is, and that's what makes magnets work. So there is no electric field.
Electric fields.
Look, electric fields Magnetic fields induce electricity. Electricity induces a magnetic field. That's how it works. There's no electricity field.
Which I traced by these mysterious seeds. So I'll give you some light that may optimize the demonstration. These seeds first have to be oriented in a way so that it is chaos. The first thing you see is I'm going to make this, I believe it's going to be a dipole first, almost certain. So I'm going to charge one positive and charge the other negative, and then we'll see how these grass seeds will form each other. Watch closely. There you go. My goodness.
Not much better than iron filings. I mean, they really should have a zoom in-y thing. But yes, it's just exactly like magnets. So if you brought two separate magnets, South Pole, North Pole, into each other, get exactly the same kind of look, except obviously they're dipoles, so the back end won't look the same, but the front end will look exactly the same.
That is a wonderful dipole field. Of course, we don't know which one is plus or minus because the grass seeds have no arrows on them. But you clearly see these incredible lines.
Again, and reality doesn't have any arrows. There's no arrows. The charges are different and the arrows are irrelevant. There's no arrows. There's no flow. There's just a change in the pressure of the amount of force of the two colors, red or black. And that's all there is.
Radially inwards or outwards on each one of the charges, and then you see these nice arcs in between. Who could see it easily? Okay, you got something worse for your tuition. Put a little bit more charge on maybe. Very clear. And now, which is perhaps more interesting, I'd like to show you the field surrounding two charges, but now the charges are both the same polarity. So we have to undo the memory of the grass seeds.
So I don't know exactly what he means by the charges of the same polarity, so well, we'll find out, maybe.
Okay, now we'll try to make them both the same polarity. And then watch this hair blower effect that I told you about. Ah, look at that. Great. Now you really clearly see these field lines, and you see in between how the...
So it's just like showing two electrons, or me taking two north ends of a magnet and sticking them together, exactly the same pattern. So again, it's a magnetic field. Electricity induces magnetism. He knows that.
The two air blowers are competing with each other. Very impressive. All right, so that's the way you see field lines now, electric field lines. And some of you may have seen with iron files, magnetic field lines.
Yeah, there's only magnetic field lines. There aren't any electric field lines. Just aren't.
If I have the Van de Graaff, and I have the Van de Graaff here, and let's suppose the Van de Graaff is positive. I don't know whether it's positive or negative. Let's suppose it's going to use the one over there. And I'm going to stand here on the ground, bolt the Lewin. What is going to happen with me? Through induction, the electrons being sucked out of the Earth and coming up because they want to go close to the positive charge.
So again, the electrons aren't moving. There's no electrons going anywhere. They're just pushing against each other, creating pressure. Electrons are being compressed into a smaller amount of space. They're being pressurized. That's it.
So, I will become negatively charged. What will the field lines do? Oh, it will be extremely complicated. Very complicated. But something like this maybe. Maybe something like this. Some may come out here. Some may end up on my neck here. Some may go here. Like so.
All right, so there are no field lines. There's just the amount of pressure. There's they're magnetic lines, if you want to call them lines, but they're just, the lines are only illustrations of how much force of a particular kind, the one sensitive to electrons in this case, is at that location, and in what direction it's moving. That's it. They're not real. There are no lines in reality.
Very complicated field configurations. But I want to probe that field. Somehow, a little. Get a feeling for what that field is like. And the way I'm going to do that is I'm going to put a charged balloon. There you see the balloon, it's a conductor. I'm going to put a charged balloon and put it here, say. Well, if it is a positively charged balloon, it will take off in that direction. Right? The force is always tangential to the field lines. It will abandon the field lines. It won't stay on the field lines. There's a lot of damping on the balloon. That's why I chose a balloon. So it will move relatively slowly.
So, again, I prefer that he would have drawn the topographical lines, because then you would understand that it's not really tangential. It's perpendicular. But anyway, doesn't really matter.
It will ultimately maybe add up on my head right here. Once it adds up on my head there, so it comes in maybe like this, now it will get the negative charge from my head, and so it will become immediately negatively charged, and so the force now will reverse and will be in this direction, tangential to this field line. And so it will go back. When it hits the Van de Graaff again, it will get positive charge, reverses polarity, and it will go back. And so it will bounce back and forth between me and the Van de Graaff, and it gives you some rough feeling of what this field configuration is.
I really shouldn't have drawn it going backwards. It won't ever go backwards. It'll just bounce this way.
Although I want to remind you that the charge does not follow exactly field lines. So I'm going to sit here, and I will be part of this. That's probably going to be positive. I will automatically become negative. There's nothing I have to do. All I turn is the Van de Graaff, and we have to put a little bit of...
I think he's adding an extra ground to himself to make sure he's well grounded.
Charge on that balloon. It will probably do that by itself, but I can always give it a little kick so that it goes to the Van de Graaff. There it goes. Oh, I had to... Because my glasses are a good insulator, so I better take my glasses off so that every time it hits me, changes polarity.
So it's not electrons being exchanged, creating a different charge in the balloon, blah, 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 blah. It's just revealing the pressure. So every time it hits, pressure's lost. You've got no pressure because you were able to get out. So you had an out for the pressure, right? Now you're the same charge as the thing you had the out with the pressure. So now you're the same charge. You repel each other, and you basically go to the... I'm almost thinking you swing past the neutral, and that means you start to induce as if you're just in the proximity. So you lose the charge so fast that you go a little past neutral. So it almost might mean that that's what's really happening, is you're going past, and now you're being inductive. And then when you're inducing, you go exactly the opposite of what the charge is. So it's probably a little more complicated than just, pressure in, pressure out, pressure in, pressure out. It overswings the neutral, and that's what gives it that little extra bit of repulsion, so it doesn't stick. It would stick if it got to the same charge automatically. It would just stick. But it's a balloon too. That's probably why it bounces a little. So what's happening is it hits, loses all its pressure, but it bounces off. So now it's going to be inductive, and so now it's going to induce into an opposite, just like the magnets induce opposites. So now it's going to become an opposite of what's affecting it, and then it's going to do what the opposite does. It goes to Lewin, and now it's going to change the polarity again, and it'll swing back and forth.
So this is the way you can do physics and have fun at the same time.
Yes, and if he moved forward and back, you would see the balloon bounces slow when he's further away and bounces fast when he's close, and it's the same thing that's happening with the repulsive pressure of electrons, for example.
See you Monday.
Okay, so on to lecture 3 and such, so forth and whatnot. Thank you very much for your attention. Sorry about that. Lighting's a little poor. Not much I can do about it. I mean, I could have turned the light off, I suppose. That's something I could have done about it, but many things. Too many details. I'm way too busy for details. Anyway, till next time.